Next exam is going to be on chapters 4 and 5. Today we're going to cover 4, chemical foundations. And then, let's see, this Thursday, next Tuesday, we'll do nomenclature. And I believe, be sure, Tuesday, yeah. Okay, I built in, a week from today, I built in a buffer day. I do that so that we're not rushed. And if I happen to go too long, I can stop, pick it up the next time we meet. So we've got a chapter 4 today, 5 Thursday, and the following Tuesday is a buffer so we can overflow then. And then we can do review on that following Thursday. And that'll set us up for the next exam. So chemical foundations. Chapter 4 in your book. In this chapter, we're going to actually get into the meat and potatoes of chemistry. Start off with learning about the elements, and you've already started memorizing your elements, I hope, with your flashcards. We're going to learn all the symbols for the elements, how the structure of the atom was elucidated, and what that helps us do in terms of reactivity among the elements. And then we're going to build the periodic table. And let's see. And then we save the naming compounds to chapter 5. So let's see. Let me show you the documents that I would hand out in class so that you can be looking for them in Brightspace. All right. Let's see. I'll set them over here. Of course, you have the PowerPoints, chapter 4. And then I would also make available chapter 5 PowerPoints. Then you would have a review document that covers chapter 4 and 5 for exam 2. And the key is a separate item in module 2 in Brightspace. And along with that key, you would have the usual worked problems in my own handwriting. If you get stuck on a problem and you can't figure it out, figure out where you went wrong, this will get you started. And then after that, if you still can't figure it out, then you bring your problems to me. Or to Barry Pine. You know, if you can't get in touch with me, Barry Pine is our physical science tutor. And his contact information is in the landing page for CHEM100 in Brightspace. Let's see. Oh, we did that already. Let's see there. Okay. I've got an extra credit project. This is the, it's called Getting to Know Your Periodic Table. And these are the instructions, how you fill out the table. And then on the second page, is a blank periodic table, okay? So you fill that out, and the whole thing's over 400 points. But that's the maximum number of points, and then I prorate them based upon how many you get right. And one more. That last extra credit project, the periodic table, is based upon material that comes out of this chapter, but you may have to go outside, look in your textbook, search on the internet to be sure you got all the information that you need to fill out the table. The best way to do that one is download the document and print it, and then take the blank table and fill it in by hand. Then scan it or photograph it and send me both the cover sheet and your finished document with your name on it. I use the cover sheet as a grading tool. Okay, then when we get into chapter 5, we're going to learn how to name compounds, and that's where this one comes in. 50 ways to name your compound. And the instructions are there on the front page. And you also have available, well, you got names and compounds. If you got a name, you write the compound in the space provided. If you've got a compound, you write the name. And this is to give you experience and practice naming compounds. The last sheet is a list of polyatomic ions, and that won't mean anything right now, but it will by the time we get through with chapter 5. Now, I would also urge you, this is an extra credit, and I would urge you with these extra credits, especially the naming compounds, don't just go on the internet and look them up and spit them out on the paper. That doesn't do you one bit of good. And sometimes I can tell when you've done that based upon the spelling. If you go on the internet and look up a compound and it spells, say, the sound of F with a PH, I know you looked it up on the internet. You got it from a website that uses the British version. And I'll count off of that one. I can't catch you at every moment of cheating, but you're only cheating yourself if you don't do this based upon the rules and not upon just looking up the information. All right. Let's see. Okay, that's it. Those two projects, those extra credit projects, the periodic table and naming compounds together will equal the weight of one exam grade. No, half an exam grade, excuse me. Half an exam grade. So you can still build up some points. All right, back to chapter 4. All right. Before we say how many elements there are, let's define what an element is. Or did we do that? We might have done that already, but it bears repeating. An element is the simplest substance that can be isolated from its surroundings and cannot be further broken down by chemical means. So if we say, I've got water, I can break water apart into hydrogen and oxygen, but I can't break hydrogen into a smaller element, and I can't break oxygen into a smaller element. At that point, we know that we have two elements together in that compound. Now, in nature, the periodic table now has 118 elements, and each one has its own name. There are no more placeholders anymore. You used to have placeholder names for the elements until the scientific community agreed upon a name for that element. So now we have names for all 118 elements, and roughly 88 of those can be found in nature. Now that's an estimate. Some estimates go as high as 98. And I think the reason that they do that is originally our analytical techniques were not refined enough to detect the very, very small amounts of some of these elements in the natural world. Now we can do that, and we find them out there in the natural world. But before that, before we found them in nature, we actually produced them in nuclear reactors. Okay. And most of those, in fact, probably all of those are radioactive. They have no stable isotopes. So a very large number of the elements, up to 98, can be found in nature, and the rest of them are absolutely man-made. Okay, if you think of chemistry in this way, we're going to learn the alphabet first. The alphabet, in English, we have 26 letters, and we put those letters into combinations that make words. And those words make sense. They convey an idea. In chemistry, we have element symbols. All right, that's our alphabet. And you're learning that now with your flashcards. Then we're going to put those elements together, those letters together, in such a way as to construct compounds. So the compound is analogous to our English word. And the elements are specific for a certain type of atom. The simplest unit of an element is an atom. And we'll talk about that a little more in just a minute. And then you put those atoms together to make a word, or what we call a compound. Okay? Then in subsequent chapters, we're going to put those words together in sentences. And sentences in chemistry, a sentence in chemistry is a chemical reaction. Okay, so that's where we're headed. There's your periodic table of elements. And I handed this out for the face-to-face students on the first day. And this is available in Brightspace. This tells you which elements I want you to memorize. If you haven't already seen this, you need to get cracking. Those that have red boxes around them are the elements that you must memorize. And that's about 60 of them. Also, the ones that have the blue squares around them, those are diatomic elements. So when somebody says, gives you hydrogen in a sentence, unless they're very specific about what hydrogen is, you must assume that it's two hydrogen atoms connected together. That's a diatomic element. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all the diatomic elements. The reason you need to know not just the symbol, but the fact that they're diatomic is that if you're given a word problem and the word problem says react oxygen gas with, I don't know, sodium metal, you know that when you write the sentence for that, the chemical reaction, oxygen must be O2. Otherwise, the reaction will not balance. You cannot balance it. It won't represent the real world, as a matter of fact. Okay. So that's the periodic table, and it's organized a certain way. We're going to get to that eventually. But first, let's talk about the abundance of elements in the universe. This table, which is from your textbook, but your version, your edition of your textbook may be later than mine, the table that's shown here, and it may have a different number. But the table is more than likely in your version, your edition of the textbook. This is the distribution of the most abundant elements in the Earth's crust and oceans and atmosphere. So we're including both the thin crust of the Earth, the oceans, and the atmosphere. We're not going below the crust into the mantle, just the crust, oceans, and atmosphere. So, and this is percent by mass, okay? Not numbers of elements, not numbers of atoms, but by mass. So, the most common element by mass on the Earth's surface is oxygen, almost 50%, 49.2%. Now, why is that? Well, several reasons. The atmosphere contains 20% oxygen. Okay. The oceans and lakes and rivers, they contain water, right? And most of the mass of water is oxygen, because hydrogen is so light. Oxygen is most, the ratio by mass here is about 1 to 8 mass ratio. So there's 8 times as much oxygen by mass in water than there is hydrogen. And then the other is crust, in the crust. Most metals, which is most of the periodic table, are combined in the Earth's crust with oxygen. This is oxides of metals, or non-metals from that matter. Let's just say oxides of elements. That includes everything. That's why oxygen is the most common element by mass in the Earth's surface. The next most common, 25.7%, is silicon. Now, why is silicon so common? That's primarily due, there's not silicon in the atmosphere or much, there's some, but not much in the oceans, but there is a lot in the crust. Silicon dioxide. Right, so there's oxygen again, but there's also silicon. And silicon forms, well, actually, it's not just silicon dioxide. There's usually a combination of several elements: silicon, aluminum, potassium, magnesium, and several others. But silicon is very common. And if you want to find a lot of silicon, just go walk on the beach. You have silicon through your toes, as far as you can see. Then the next most common is aluminum, because of this combination of aluminum in the Earth's crust along with silicon. Iron is a little less common. These elements are largely found, iron, calcium, sodium, potassium, magnesium are largely found in the Earth's crust. Sodium is in the oceans, right? Salt water, sodium chloride. So that's another place you can find sodium. Hydrogen by mass is not that prominent because it's just, there may be a lot of hydrogen atoms, but they just don't weigh much. And then you've got the other minor elements. So the most abundant by mass is oxygen, then silicon, then aluminum, and then iron. Okay, we defined the element just a few minutes ago. But when we say element, it could mean a single atom, or it could mean a collection of atoms that are alike, that are the same, right? So, and we use a symbol for each one. So this would be my symbol for an atom of hydrogen, or my symbol for an atom of carbon. Okay. Or it could be in the case of hydrogen, we would want to write the molecule like this. Now, what's a molecule? A molecule is a combination of two or more atoms that behave as a single unit and have a unique chemical identity. Okay, so they act like a single unit. Molecule of water has two hydrogens and one oxygen. Molecule of nitrogen has two nitrogen atoms. A molecule of glucose that's floating around in your plasma and providing energy to all your cells is a combination of three elements. Right? 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. That's a molecule of glucose. It could also mean atoms of the element are present in some other form in your body. These would be neutral, right? But you could also have ions of those elements in your, say, in your body or in the natural environment, right? That one could have a plus charge, right? Or you could have this in your system, right? Or you could have this in your system, or you could have this in your system, or you could have this in your system, right? And those for perfect health, there's a certain range in which those should be in your system, usually measured in your blood. And anything above or below that would put you in distress of some kind. Okay, the symbols for the elements, I've been using them here, but the symbols from the elements were proposed by a Swedish chemist named Berzelius. There were a number of different proposed systems for representing the elements. And some of them are pretty off the wall, so to speak. One of them in particular was inherited from the centuries of alchemy, but it wasn't very user-friendly. This one is user-friendly. The one by Berzelius has either one or two letters. If there's one letter, it's always capitalized, like carbon or hydrogen or chlorine or sodium or potassium. One capital letter. If we have another element that we want to start with that same letter, then we have to add a second letter to it. And the second letter is always small. So if I wrote something like this, there's magnesium. If I wrote this, that would be nothing. That does not properly represent magnesium. Capital letter, small letter, if there are two letters. Okay. Many of the elements in the periodic table and their symbols can be traced from their English names. So when we say calcium, the first two letters in the English word calcium. But that's not always the case. Well, there's krypton, right? That's simple, right? But sometimes we use a Latin, usually Latin, sometimes Greek name. And we take letters from the Latin or Greek name to represent the element. And I think we've probably got samples, examples here. Gold, my favorite. Au is aurum. That's Latin for gold. Or lead, which is Latin plumbum, which actually means heavy in Latin. So there's a certain logic to it also. There are other elements like iron, right? Copper, right? Copper is not CO. CO is cobalt. Copper is Cu because its Latin name is cuprum. And iron is ferrum, 2 R's. So there's several of those in the periodic table that I want you to memorize. And that's why the flashcards are necessary. You just instantly know when you see the name iron that it's Fe. Or if you see Fe, you instantly know that's iron. Okay. Here's a list of the common elements. And when you make your flashcards to memorize the elements, if you go to that periodic table where I have the red boxes, then you'll only find the symbols. So that means for those symbols, you've got to go look up the name. And table 4.3 will have most of them. Most chemistry texts also have a complete list of the elements inside either the front cover or the back cover in alphabetical order. All right. Now let's, the heading for this section is Dalton's atomic theory, but we need to get some of the laws in hand. Remember what a law is. A law simply says, this is what happens under these circumstances. I don't know why. It's just a statement of fact and outcome. So let's cover some of these laws. They're instrumental in a historical sense to understanding how elements behave. The law of conservation of mass, Antoine Lavoisier. He was French. And notice the year, 1773. Okay, he proposed this law of the conservation of mass. It just simply says, during a chemical reaction, and how do we define a chemical reaction? We have reactants coming together, and they each have their own individual identity, right? Their reactivity, other factors, other physical factors, chemical factors, properties, I should say. Chemical properties, physical properties. After the reaction, the products have recognizably different chemical and physical properties. Now, some of the properties may be similar, but they are unique products. That's a chemical reaction. What Lavoisier said was, during that process, that chemical reaction, if you account for all the mass of your reactants, then you'll have exactly the same mass in the products. If the mass of the products happen to be less than the mass of the reactants, then you're not accounting for every product that comes out of that reaction. But basically what it says is that in chemical reactions, matter is not created and it's not destroyed. Okay. Unfortunately for Lavoisier, he was active during the time when the French Revolution got rolling. And before the Revolution, Lavoisier, who was reasonably wealthy himself, but he thought, you know, he could create another stream of income, bought a contract from the king of France to collect taxes for the king. That's the way they did it in those days. You paid the king a certain amount of money, and the king gave you the right to collect taxes from this population. And when the king said, I need this much money from your taxes, then you gave him that money, and anything extra you collected was yours. That was your profit margin. Well, most people didn't care for tax collectors then any more than they do now. Unfortunately, for Lavoisier, the King of France was imprisoned, and later he and his wife were beheaded with a newly invented device by Dr. Guillotine. So Lavoisier had been a tax collector, and that stuck to him like glue. And people who wanted to get even with him, the people in charge of the Reign of Terror, the French Revolution came in stages, but eventually they reached a point where there were just a few members of a tribunal at the top, and all they had to do was write your name on a piece of paper and you lost your head. Well, Lavoisier was one of those. It was get even time, I think. Okay, after Lavoisier, then along comes an Englishman by the name of Joseph Proust. And Proust proposed that this law of constant composition. And what he said was, if you have identified a compound, and you know it's a compound because by chemical means, you can break it apart into elements. Once you've identified that compound, all of its chemical and physical properties, it doesn't matter where that compound comes from, either from a chemical reaction or purifying it from a natural source, like pure water from seawater, we distill it, or tap water, we distill it and get pure water. Or you can react hydrogen and oxygen together and produce water. That, gas. And at those temperatures, that's going to be a gas too. Anyway, whether you purify it from a natural source or you make it by chemical reaction, the mass composition of that compound is always the same. Right? So the ratio of oxygen to hydrogen here is 8 grams of oxygen for every 1 gram of hydrogen in that compound. And whether it comes from this source or any other source, it's always the same. That's definite proportions or constant composition. I've heard it actually definite composition also. So don't be thrown if you see it in any one of those 3 ways. Okay. Carbon dioxide, similarly, has a definite ratio by mass. Now, it's important to recognize that in the 1800s, the 18th century, late 18th century, during this time, actually into the early 19th century, chemists only understood mass ratios of the elements. They had no concept yet of atomic ratios, right? We look at it now and we say, okay, 2 atoms of hydrogen and 1 atom of oxygen makes water. But in their days, all they knew was 8 grams of oxygen and 1 gram of hydrogen come together in that form. All right. So that later on, we'll see that was a disadvantage. John Dalton then proposed, not too long after that, the law of multiple proportions. So he was taking off this fact of constant composition and said, rather than constant proportion, we have multiple proportions if you have a series of binary compounds. What do I mean by binary compounds? They're made of 2 elements only. And I like to use this example. We now know that nitrogen and oxygen can combine like that, or like this, or like this. Actually, it can do this also. But what John Dalton was saying was, he noted that when you compare the mass ratios, and the mass ratio would be, say, 14 here, 14 grams to 16 grams. That would be the ratio for this compound. 14 grams of nitrogen, 16 grams of oxygen would be the correct ratio by mass for nitrogen monoxide. If you have nitrogen dioxide, it's 14 grams and 32 grams of oxygen. Okay. If you have nitrogen trioxide, you have 14 grams of nitrogen and 48 grams of oxygen. We could go to this one. That's this would be 28 to 16. But it's easier to see it here. Let's concentrate on those three. What Dalton said was, if two elements form this compound, then, and the ratios of their masses are fixed, then if you have the same, if you adjust the ratios so that you have the same mass of one of the elements, then the other elements in their sequence are whole number multiples. So if this one's 14, 14, 14, that one's 16 times 2 is 32 times 3 is 48. It's a whole number multiple. All right. Now, those were laws. Dalton is going to take those laws and a couple of other laws, actually, and try to put them into a coherent model, a theory, explaining why these laws work. The laws are established. Now we need a theory to explain why they work. And that's Dalton's atomic theory. Okay. These are what we're numbered are postulates. In other words, when you have a theory, your postulates say this is what defines the theory. He started by saying most natural materials are mixtures of pure substances. Let's see, I want to check on something. Right. Most natural materials are mixtures of pure substances. There are a few elements in. Now, pure, let me define a pure substance. A pure substance can either be an element or a compound. An element obviously behaves with its own chemical priorities. Compounds have their identity also, and they're pure substances. Say if we have purified water, right? If we distill water, then we have pure water. And then you can take pure substances and combine them in such a way as to make a mixture. I think, didn't we cover that before? In previous chapter. I could be mistaken. There's the calculation. Yeah, I think we did. Well, it doesn't hurt to refresh. But Dalton said most natural materials are mixtures of pure substances. So we know not to drink ocean water, right? Because it's salty. We need to drink fresh water from a river. We don't drink salt water because it's a mixture of water and various salts. Sodium chloride is the dominant one. Okay. Pure substances are either elements or compounds. and that a given compound always contains the same proportion by mass of the elements. So these postulates are really restating what we already know. But it's important for Dalton's theory to get these facts in order and have them there as part of the theory so that we can progress from there into the whys things happen. Well, okay, I misspoke. Those three statements are the problem. And Dalton's solution to that problem is his atomic theory. Dalton's going to explain why we have conservation of mass, we have definite proportions, we have multiple proportions, at least those three. So Dalton's first postulate was actually borrowed from the ancient Greeks. Elements are made of tiny particles called atoms. The ancient Greeks, well, some of the ancient Greeks believed that this was true. Right? In Greek, tomos means to cut or divide. And a means not. The prefix a for a Greek word means not. So if you've had biology before, you know that there are two types of reproduction in the biological world. There's the sexual reproduction where you have male, female come together, and you have asexual, not sexual. A fungus creates spores, right? It doesn't need a male or a female to produce the spores. Okay, so this idea came from the ancient Greeks, and Dalton just borrowed it. Now, the problem with the ancient Greek idea of the atom is they thought, or some of them thought, not all of them subscribed to the atomic theory of ancient Greece. But those who did subscribe to that theory said that everything's made of an elementary particle. Everything's made of the same particle. They were half right. And this elementary particle was not the same for every substance. So what the ancient Greeks had to do was jump through mental hoops, go through astronomical feats of mental gyration to make their atomic theory work. And of course, it never did completely and adequately explain the natural world. But when Dalton came along and said that elements are made of tiny particles called atoms, he didn't stop there. He qualified that statement by saying that all atoms of a given element are identical. But atoms of two different elements are different atoms. Okay? That solved the problem that the ancient Greeks couldn't solve. So here we have an artist's rendition. All right. So there we have atoms of each element. Notice that the red ones are oxygen, the blue ones are nitrogen, and they're different. They're different colors for a reason, because they're different atoms. Dalton also said that compounds are formed from the combination of these atoms of different elements. So a compound must contain two or more different elements. Okay? If it doesn't have different elements, it's not a compound. If it has two elements, two atoms of the same element, then it's still an element. Like O2 is oxygen. Okay? And the given compounds have unique identities not just because of the different elements that are combined, but because of the ratios and the arrangements of those elements. So nitrogen monoxide, or nitrous, see, that's not nitrous, it's nitric oxide, NO, has a unique chemical identity. Whereas N2O, or nitrous oxide, laughing gas, has a different chemical character. They're made of the same elements, but they're not the same proportions. Then Dalton went one step further. He said when in postulate 5, he's covering the law of conservation of mass. In other words, atoms are not created or destroyed in a chemical reaction. They're only rearranged. So if you have the same number of elements, the same number of atoms of each element in the reactants, then you have exactly that same number in the products. A chemical reaction then is merely rearranging the atoms. In other words, you swap dance partners, for instance, and that would give you a chemical reaction. All right, that's Dalton's law, Dalton's theory, atomic theory. So let's see if we got anything out of this. Which of the following statements regarding Dalton's atomic theory is still believed to be true? Well, answering this question is going to introduce another topic that we're coming to right after this slide. Elements are made of tiny particles called atoms. Yep, that's true. All atoms of a given element are identical? No. And we're going to talk about that in a minute. They're called isotopes. A given compound always has the same relative numbers and types of atoms? Yes. And atoms are indestructible? No. With qualification. Atoms are indestructible in a chemical reaction, but in a nuclear reaction, they can be destroyed. So actually, to be by the strict definition, only Roman numeral 1 and 3 are still true. All right, we're going to get to isotopes in a minute, but first we want to cover compounds. And I gave you that definition already. This is just a different version of it, and maybe it makes more sense. We represent the compound by a chemical formula. We use the symbols of the elements and how many there are in the compound. So I think I've got a slide on that, but it may be yeah, it comes later, but I think it's more useful now for me to explain the use of chemical symbols. Let's say this is an element, an atom of an element, and it doesn't matter what it is. Each of these four corners is reserved for a certain type of information. In this corner down here, we have what's called Z, or the atomic number, which is the number of protons in that atom. We haven't broken it apart yet, have we? No, I may be getting ahead of myself, but that's okay. Just hang on to this and we'll explain what we mean by protons. This one is the mass number. And that's equal to the number of protons plus the number of neutrons. This is reserved for charge, and this is reserved for a number of atoms. So the reason I said that was when you write the compound, you simply say how many atoms of each one is in the compound. So in this sulfur trioxide, we have one sulfur atom. Notice we don't write the one. If you got a symbol there, it's at least one atom. So we don't, that'd be redundant. And we have 3 atoms of oxygen. Okay. Like that. Okay, if we were to write the formula for this compound, DDT, and it's not important what DDT stands for right now, we're told that it contains 14 carbon atoms, and it has 9 hydrogen atoms, and it has 5 chlorine atoms. There we go. That's the formula for DDT, the molecular formula for DDT. It doesn't tell you anything about the structure of the molecule, but it does tell you the number of atoms of each element in that molecule. Okay, now we're going to get to the structure of the atom. We're going to go back a little bit. After Dalton's theory, atomic theory, to a time when electricity was all the rage, right? In the scientific community and in the social community. Right? Electricity was a phenomenon that rich people loved to have at their parties. J.J. Thomson took advantage of one of those devices that was constructed using electricity. We knew at that time we could make what we now call batteries. They were called galvanic cells, but batteries would give you a positive charge, say on that side, and a negative charge on that side. So you could run them through a light bulb or something else and make it happen. Or in Thomson's day, you could run that electricity through this glass tube, right? And you could connect the negative here and connect the positive here, and you could get particles. With high enough voltage, you could get particles going from this side to that side. And that's what Thomson was investigating. What are those particles? Well, with the cathode ray tube, he eventually proposed that those particles were negatively charged, and he called them electrons. And that's not all. He said that those electrons originated from within the atom. All right, that was earth-shaking. If these particles came from inside the atom, that meant that the atom was no longer just a jelly-filled bag. It had different types of particles inside, subatomic particles. So what that meant was, for an atom, if it has electrons in it, with a negative charge, there must be a balancing positive charge, because not only did we know about electricity then, we knew about neutrality. If you have excess of one charge or the other, you've got static electricity. So we had positives of equal magnitudes in there somehow. Question was, what were those positive charges attributed to? Right. Well, there's your cathode ray tube. I think I've got a video coming up also.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery. and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 mm Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
All right. So they knew that these were very, well, they don't know what size particles they are yet. They were small particles by mass. And actually, J.J. Thomson, with his experiments, determined the ratio of charge to mass for the electron. He didn't have the technology at the time to determine the absolute mass of the electron, but he did determine the charge to mass, or mass to charge ratio. Okay, so the proposed model from the atom now included subatomic particles, right? And we're not sure whether the plum pudding model came from J.J. Thomson or from William Thomson, Lord Kelvin, but it was circulated in around 1904. This plum pudding model simply said that the particles were the electrons, and the positive charge was distributed throughout atom. Right, so it's evenly distributed throughout, just enough charge so that it would balance the particles. Well, there was a problem with that theory. It did solve the neutrality problem, right? Equal positive charge to negative charge made a neutral atom. But this plum pudding model did not account for the mass of the atom, because J.J. Thomson determined that charge to mass ratio, and it was implied from that the mass of electrons were very small. From various experiments that were conducted on the cathode ray tube. So this plum pudding model had holes in the theory, or the model, yeah, the theory. So it stood for a little while, and it was called plum pudding model because if you've ever had plum pudding, little pieces of plum are scattered throughout the pudding, and that's like, those are the electrons. Now we're going to get an idea about the mass of the electron with experiments from Robert Millikan. J.J. Thomson was English, Robert Millikan was American. And he conducted experiments often called the oil drop experiment, and determined the mass of an electron. And it turned out to be very small. The magnitude of the charge on a single electron, he determined by his experiment, was 1.6 times 10 to the minus 19th Coulomb. And a coulomb is just a unit of measure for charge, but it's very small. And then he used that coulomb in this equation. There's a value over here for the ratio. He used the charge and the value for the ratio and determined the mass by that calculation. I think I have a video about that. Just a second. The mass of the electron is 10 to the minus 31 kilograms. Very, very small. And his work on the electron won him the Nobel Prize, including the work he did to verify experimentally Albert Einstein's equations on the photoelectric effect, for which he won a Nobel Prize, I think, 2 years earlier. Okay. So let's start this video. This is an artist's idea of what the oil drop experiment looked like.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay. That's an important factor. It's such a small mass, it does not account for the mass of the atom. So there's part of this puzzle is still missing. Along came Ernest Rutherford, an Englishman. He did not subscribe to the plum pudding model. He proposed another model that accounted for the mass of the atom. It was called the nuclear model. And he said his model, his proposed theory was that the atom is composed of a very dense nucleus which housed the positive charges. Okay, and the negative charges were out here somewhere. I guess we need 3 of them. So most of the mass of the atom is in the nucleus, and most of the volume of the atom is empty space, or space occupied by very, very light particles, the electrons. So his experiment the particle that he was proposing in the nucleus was a proton having the same charge as the electron, but a much, much greater mass. So his experiment was designed to test whether the plum pudding model or the nuclear model was the accurate one. In order to do that, let's see, do I have a video on that one? No, I don't have a video, so we're going to use this schematic to show us what happened. By this time, the early 20th century, various forms of radiation had been identified by several researchers, but I think Henri Becquerel proposed these three main types of radiation: the alpha, the beta, and the gamma. Gamma is light, very high energy light. Beta is high-speed electrons. Alpha is a helium nucleus. Okay, we know that now. Back then, they just knew it was a heavy particle. And that was enough for Rutherford. He just needed something that he could fire at the atoms and determine whether his model or Thomson's model was the accurate one. So what he needed was a target. Well, he needed a source of alpha particles, obviously. So he found that. And that he encased in lead, so that they would only come out one side. And then he needed a target. He didn't want the target to be very thick, because if it were thick and his model was correct, then there'd be too many atoms in the layers and they'd stop all of the alpha particles, nothing to get through. So he needed something very thin, just a few atoms thick. And in those days, it was common knowledge, and the technology was there to produce extremely thin gold foil. So that was his target. Gold foil. Just a few atoms thick. Okay? So these alpha particles came streaming out of here. They could have come out like that, or they could have come out like this. So we needed to straighten them out. We call that collimation. And the best way to do it, the easiest way, is to put a slit here and another slit here, lined up perfectly. So only the ones, you could get one coming through here like that, or like that, or like this. Only the ones that came through here and were lined up with that slit came out that side. So now he had a straight beam of alpha particles to fire at his target. Now he needed a detector, right? Now, in this schematic, we have a detector that looks like a telescope, but it's more likely that he used photographic plates around the target. Most of the alpha, if his theory were not correct, if Thomson's plum pudding model were correct, then all of the beam would go straight through and be detected right there. Because the electron was very small, had very little mass, and the mass of the rest of the atom was scattered throughout that pudding, right? So even if it slowed the beam down, they would still go straight and hit the detector on the other side. If Rutherford's model were true, this is the hypothesis. If my model is true, then we're going to get some deflection. These positive charges are going to come in here, and when they encounter the negatives of the electrons, they'll be deflected slightly. Like this. Maybe even a little bit more. And then if some of those particles actually strike the nucleus, which is extremely dense and massive, then we're going to get deflection. Even some of them bouncing almost straight back. So that would be the way to test the hypothesis. Which one is true? And as it turns out, Rutherford's nuclear model was correct. And from when he published that work, the plum pudding model was dead. Remember? When you have a theory, if the theory doesn't work, you have three options. Well, actually four, but three primary. You can either modify it, you can restrict its use, or you can throw it out. And that's what they did with the plum pudding model. They threw it out, it was dead. Now the nuclear model was the basis for all future research. Okay. So Rutherford got a Nobel Prize for his work with this line of research, and his publications proved the structure of the atom was nuclear based. And that's an animation showing what you might have seen. Okay, another animation. Yeah. Okay, that's enough of that. Okay. Oh, I do have video. It's not narrated, so you just watch it and you'll see all the parts of the experiment contained in this representation. So this is to summarize what we have learned, and then we're going to take it a step further. But at this point, we know that all elements are made of simple particles called atoms. We also know that the atoms are, during a chemical reaction, remain intact, but they can be broken apart, and they're constructed of subatomic particles. Now, as far as chemistry goes, those subatomic particles are useful for understanding why reactions occur. But the chemical reaction itself does not break the atom apart. Now we have a nuclear model for our atom, thanks to Ernest Rutherford. And let's see, I left one out. Rutherford's graduate student, and later I think he was a postdoc for Rutherford, named Chadwick. Chadwick, I believe. Rutherford knew from his calculations that his nuclear model was not complete. He had accounted for the he had accounted for the charge balance in the atom correctly, and where those charges were located. But he had not accounted for all the mass of the atom. All atoms except for one, hydrogen, have more mass than can be accounted for by protons only. There's another particle in there that he proposed was equal, almost equal in mass, but with no charge. And he gave Chadwick the task of proving it. So Chadwick did. And he discovered and proved that there was another particle in there just slightly more massive than the proton that accounted for the rest of the mass of the atom. And Rutherford got a Nobel for his work. Chadwick got a Nobel for his work. And now we have all the three elementary particles that are present in the atom, down to a certain level, right? As it turns out, those subatomic particles can also be broken into subatomics. But we're not going to go there. Now that we have the neutron, the proton, and the electron, we can, for chemical purposes, describe each of the elements. The modern concept of the atom now goes beyond particles. In fact, the idea of particles in an atom, while they are physically accurate, they're real, but sometimes these particles behave like waves, and many times they're better described as waves, especially the electrons, rather than the planetary model where you have, say, for hydrogen, you have a proton there, and then you have an electron out here. And Niels Bohr proposed the planetary model, where the electron was out here and the proton was in the middle. It was consistent with Rutherford's atom, but it only went so far. And it didn't completely explain the behavior of electrons. Now, without getting too far into the weeds, what we arrived at eventually was describing the electron as a wave rather than a particle, kind of like light beams. Light beams can be, light can be described as a particle or as a wave, and sometimes both. So what we need is a wave at a certain distance from the nucleus that has a perfect number of wavelengths in that space. And now this is three-dimensional. I'm representing this two-dimension, but three-dimensionally the wave exists. And to make things even more problematic, the description of the atom now is based upon probabilities. This is the progression that we went through to get to our modern concept. And this is a little chart I found online. It's created by, oh, what was the man's name? Shoot, I can't remember. Compound interest is his the title for his project, but I can't remember the man's name right now. And he put this thing together. It's fairly nice. I mentioned Niels Bohr. There was also an Erwin Schrödinger who was instrumental in developing what's called quantum mechanics. Right. But for this course, we don't want to go too deep into that topic. It's just there if you're interested. Oh, I do have a slide on Chadwick. So Chadwick came along and discovered the neutral particle, the neutron. And that completed the description of the atom for our purposes as chemists. All right, electrons, that's where they are. Protons, that's where they are. Neutrons, that's where they are and what they do. Now, just a second. Yeah, okay, we are going to get to that discussion. Okay. So the nucleus nucleus is very small in volume compared to the overall size of the atom, but it contains most of the mass. It's very, very dense. Now, you may be wondering, once we get larger and larger atoms that have more and more protons in them, how do you keep those protons together, right? Because like charges repel. So how do you keep all those protons packed into that nucleus? Well, as it turns out, that's what the neutrons are for. They provide the glue that holds those protons together. All right, relative masses, notice that the neutron is a little heavier than the proton, and both of them are about 1,800 times as massive as the electron. Now, why do different atoms have different chemical properties? Right, that's really the question. Think about it. When two atoms approach, if they're going to react, if they're going to combine, or if they're going to do anything at all, what do they see first? As they approach, they don't see their nuclei first, they see the electrons first. So electron interactions, that's where chemistry happens. And there are a number of theories that have been proposed over the years about how this interaction occurs. Very simple models at first, and then more, we have to actually change the model and make it more complex and more based upon probability eventually to get an accurate estimate of how the reaction occurs, the energies involved, and the expected outcomes. And that's where quantum mechanics comes in at the end of the road. All right. Now, these elements composed of atoms have a definite fixed number of protons. In other words, if you have a certain number of protons, you will always have that element. So 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium, 4 protons is beryllium, and you just keep going. Every time you add a proton, you get a new element. Now, to make up the mass, of course, you need to add neutrons. And you can have a certain number of neutrons, or you can have a fewer than or greater than. And if you have an element, an atom here, with the same element of the atom here, but they have different numbers of neutrons, then you have isotopes. Chemically, they behave very similar. But physically, they have they're different, slight differences, because they have different masses. The mass difference is due to the number of neutrons. If you change the number of protons, you change the element. All right. Most naturally occurring elements consist of a mixture of isotopes. For example, let's see, chlorine has 17 protons. Now, one isotope of chlorine will have 36 mass number, which means what? That's 19 neutrons, right? This is the number of protons. This is protons plus neutrons. So you just subtract protons from that number and you get the neutrons. This isotope of chlorine has the same number of protons, but it has one fewer neutron. 18 neutrons. Right? They're both still chlorine, and they're both present in naturally occurring chlorine. And in this case, they're approximately equal numbers. That's not always the case, but for chlorine, that's true. Sodium's another example. 11 protons automatically. Sodium. Can't be anything else. But one isotope has 12 neutrons and the other isotope has 13 neutrons. So that gives the mass number for one, 23, and for the other, 24. So here's our symbol. I left some things out. Z is the atomic number. X is the symbol. A is the mass number, which is protons plus neutrons. And they left out the charge and the numbers positions, but those 4 positions around that symbol are reserved for specific information. Okay, here's carbon. Carbon will have 6 protons. And for this example, it has how many neutrons? It has 8 neutrons. That particular isotope of carbon is radioactive, right? You've heard of carbon-14 dating. It is radioactive. In other words, it spontaneously transforms into some other element. Right? It's not stable. The symbol is C for carbon. It has 6 protons. It has 8 neutrons. Now, the more stable isotope of carbon is carbon-12. It has the same symbol, 6 protons, and 6 neutrons. And most of carbon in the natural world is carbon-12. Okay, let's see if we can solve this problem. We got 20 minutes to go. If we have an isotope of X containing 23 protons and 28 neutrons, plus 28 equals 51. All right, so there we go. Got 51 there. Question, what's the mass number of this isotope? 51. 23 plus 28. Okay, identify the element. How could we identify the element? Well, the mass number is 51. The element is based upon the number of protons. So we go to the periodic table and we look for the number of the atomic number. The one on the wall over here has, at the top of each of the squares is a red number, and that's the atomic number. And if we go find 23, we find it's vanadium. Like that. Okay. All right. Now let's talk about the periodic table. The periodic table like most scientific developments, didn't just sprout full blown from somebody's head. It took a sequence of discoveries from other scientists over the years to come to this point. This was the first periodic table published by Mendeleev, Dmitry Mendeleev. And remember, at this time, they didn't know about atomic numbers. They didn't know about subatomic particles or numbers of atoms. They only knew mass. So he was arranging these elements based upon sequences of masses increasing for the elements and similarities of chemical and physical properties. That's how he grouped them. And the groups in Mendeleev's first periodic table were left to right, whereas in the modern periodic table, the groups are vertical. Now, in Mendeleev's second publication, he rotated it 90 degrees and put them in the order, in the same relative positions that we know today. So if we take example here, let's see, carbon 12, that's a relative mass number, which is accurate for what we know about the mass of carbon. We also know that the next element in the group below carbon in our table is silicon. And relative to this mass of carbon, silicon has a mass of 28. Right? They're all relative. But notice the next mass is 70. Right? But there had not been, if we follow the trend as Mendeleev did, there should be an element there with a mass number of 70. But there's not, because it hadn't been discovered yet. So he left that blank. Then he came down to 10, and it should be in the neighborhood of 118, which it is. Okay. So Mendeleev organized his table, and we organize our modern table based upon groups and periods. Okay. This is his second publication. It's a little hard to follow, but I will call attention to the ones where there are questions, were those elements that were left out. Now, what Mendeleev did do is when he came to a place where there was supposed to be an element, but there wasn't, instead of moving the next one in the sequence over to that place, he left it blank because the next element did not have the proper chemical and physical properties to fit that space in the group. So he moved it over into the group where it did have the similar properties. And he said, someday somebody's going to find an element with this mass and with these properties. And they did, every time. That's why Mendeleev gets credit for the periodic table, because he used it to predict undiscovered elements. All right. Now here's a modern table. And notice that we've got it arranged in such a way that similar elements, that is, elements with similar chemical properties, are in groups, vertical groups. Right? So on the far right, we have noble gases. They have similar properties because they don't react with anybody. Or in the first group, leaving hydrogen out, over on your far left, we have lithium, sodium, potassium, rubidium, cesium, francium. Those are all alkali metals, and they behave similarly in chemical reactions. So they're in the same group. Now that's an explanation of groups. Let's see. I'm going to talk about periods. Let me be sure. Okay. Let's see. All right. Let's give Henry Moseley some credit here. Eventually, Henry Moseley was an Englishman, a very young man, who worked on X-ray stimulation of metals primarily. And he used the X-ray stimulation of the metals to produce spectra. So the spectrum that was produced by stimulation of these elements, he could identify lines in their spectra, And he picked one in particular, and he came up with a formula that would predict the wavelength of that particular line. And all he had to do was for each element, change one number. So he had some formula out here, and he had this number here, and it would give him the wavelengths, whatever that formula was. All he had to do is change this, and it was unique for each element. It was a whole number. It worked every time. He called that the atomic number. Right? Now, he didn't draw the connection between the atomic number and the number of protons, right, yet. That came later. But as it turns out, the reason that this worked is because it represents the exact number of protons in that element. So Henry Moseley did this work. He was a very young man. And notice 1914, World War I starts. He's a patriotic Englishman. He joined the army. He went off to, I think it was Gallipoli, and was killed. So that's the end of his career. But he did give us this much. Okay, when you look at the periodic table now, the modern periodic table, you can find it's divided into metals versus non-metals. It's divided into groups or vertical families. And its horizontal lines, rows, are periods. Okay, and here's what it looks like. If you notice this dark black line that goes between boron and aluminum and then stair steps down like that. That divides non-metals on the right from metals on the left. So notice most of the periodic table is metals. Now, there are some elements that are very close to that black line that in some chemical reactions, they behave as metals, and others they behave as non-metals. Those are called metalloids, like silicon, germanium, arsenic, antimony, tellurium, and polonium, and astatine. So if you're going to fill out that periodic table, I ask you to draw that line in there. Pay attention. It might not surprise you how many students get that line wrong because they don't pay attention. Okay. The periodic table is also divided. It has vertical groups, and some of those groups have names. Let's see, is it on the next slide? Non-metals. Okay, metalloids. That doesn't help much. Yeah, you have different metalloids. It depends on the author as to which ones are metalloids. All right. All right, let's go back to this one. Notice that in this particular periodic table, the very far right-hand group are noble gases. Right next to them, left of them, are the halogens. Next to those are the oxygen group. They're called chalcogens. That's the oxygen group. Next to those on the left are the nitrogen group, or the pnictogens. Okay. And then if you go to the far left, you get the first row, which are the alkali metals. And that does not include hydrogen. Hydrogen is placed over there just for balance, right? Hydrogen is a special element all to itself. So the alkali metals start with lithium and go down. The alkaline earths start with beryllium and go down. And then there's a group in the middle called the transition metals. Transition elements, transition metals. And they do this, that. They transition from one side to the other. if you combine both the left 2 rows and the right 6 rows, these are called representative elements. Then when you get down to lanthanum, number 57, there's a gap between 57 and 72. And that's filled in by the lanthanides, those elements. The reason we pull them out, well, 2 reasons actually. That keeps the periodic table from being as wide as the wall. And it also is based upon their electronic structures. The lanthanides have a particular structure that's characteristic of all of them, and they're separate from the transition metals. In fact, they're called the internal transitions. And then next below lanthanum is actinium, and the actinides are like that. And part of the actinides are uranium and plutonium, right? I want you to memorize those simply for their historical significance. The uranium bomb, little boy, destroyed Hiroshima. The plutonium bomb, Fat Man, destroyed Nagasaki at the end of World War II. All right. Most elements are very reactive, which means that most elements are found in compounds, right? And we know that from our previous discussions, from Dalton's observations. Right? There are very few that are found in uncombined form. The noble metals like gold, platinum, and silver can be found as nuggets or flakes. Noble gases, definitely. By the way, the noble gases start with helium. That's the lightest one, right? Where do we find helium? Well, helium was first identified on the sun, spectroscopically, just looking at the light spectra and splitting the light open and seeing what the lines were. That's where helium was found first, and then it was located on Earth eventually. But when we obtain helium from our natural sources, we don't get it from the atmosphere. It's so light that it's long since just completely evaporated. It's out in space. There's a little bit close to the Earth's surface, but most of the helium that we get comes from natural gas. When natural gas comes out of the ground, it has contaminants, moisture. We have to remove the moisture, any particulates, and it also has some helium in it, much more helium by volume than you find in the atmosphere. So we extract helium from natural gas and store it underground for strategic purposes. All right. These are the diatomic elements. I mentioned those earlier. And most are gases, bromine's liquid, iodine's a solid at room temperature and pressure. Now, some elements have different forms. And when I say some elements have forms, I mean, they are still elements. In other words, there's only one type of atom in that form. And these are called allotropes. Examples: carbon. Solid carbon comes in 3, actually more than 3 forms now. Diamond is pure carbon, assuming it has no added elements or inclusions, fractures, or anything like that. Diamond is a network solid. In other words, each carbon is bound to 4 other carbon atoms by a bond that's so strong It makes diamond the hardest naturally occurring element. Substance, actually. So that's one form of carbon. Another form is graphite, right? Graphite, like you find in lead pencils. There's another one that was discovered back in the early 20th century called Buckminster fullerene. They call them buckyballs. They're spherical in shape, but they're only carbon. And they're composed of 60 carbon atoms in that ball. We also have carbon nanotubes, right? That's a different allotrope of carbon. They're used in some form of nanotechnology. Some of them impregnate your clothes. All right. That's what diamond and graphite look like. Graphite's in layers. Diamond is three-dimensional network. And there's your buckyball. Show it again. Come on. Oh, and there's the nanotubes. Okay. How do we make ions? Oh, let's see. I'm about out of time. Ion. You know, I'm so close to the end, I'm going to keep recording. Since there's nobody in the class and nobody, you don't have to get up and leave. I'm going to keep recording and finish this chapter. That means the next 2 times we meet, we can spend all the time we want on chapter 5. How do we make ion? Since the atom, we start with a neutral atom. In other words, equal numbers of protons, equal numbers of electrons. In this case, we're using magnesium with 12 protons and 12 electrons. So it's neutral. It has no charge. You can do that or just leave it blank. Now, how do you get an ion of magnesium without changing magnesium into something else, into some other element? If you mess with the positive charges, then you got another element. So the only way to make an ion is adding or subtracting electrons. And for metals, they want to give up electrons. So we subtract electrons. In this case, magnesium prefers to lose 2 electrons. So now we have an excess of 2 protons. We've got 12 protons, 10 electrons. Okay. That's a magnesium ion because we modified the number of electrons. Okay. Metals tend to lose 1 or more electrons to form positive ions, and these are called cations. Okay. All right. For nonmetals, they tend to gain electrons. So for instance, chlorine has 17 protons. That means it has 17 electrons. That's neutral. So it likes to gain 1 electron to 18 electrons. What does that mean? Now we have an excess of 1 electron, 1 negative extra that's not balanced by a positive. So chlorine forms a -1 charge by accepting 1 electron from somewhere. And we'll talk about this later. When we put it in the name of a compound, we change the ending to IDE. So chlorine is chloride. Therefore, we call this sodium chloride. Now, some of the charges for our ions can be predicted from the periodic table. Those are the ones that have fixed. They always form the same ion every time they undergo a chemical reaction. All right. The alkali metals, the very first column on the left, the alkali metals are 1+ charge. Their next door neighbors, one column over, the alkaline earths, they always form 2+ charges. The halogens on the far side next to the noble gases, of course, the noble gases, they normally don't form ions. I mean, you can force them, but during chemical reactions, they typically don't react, right? They don't form ions. But their next door neighbors, the halogens, always accept 1 electron. And then next door to them, the chalcogens, the oxygen group, they always accept 2 electrons. They have a 2- charge. Next to them are the pnictogens. They have a 3- charge. And aluminum, gallium, indium in that column, they always form 3+ charge. There you go. Now they got boron in there. Boron is little, since it's a metalloid, sometimes it forms a charge and sometimes it doesn't. Okay. Let's see if we can use what we've learned to answer this question. An ion with a 3+ charge contains 23 electrons. So we know our ion has a 3+ charge and that it has 23 electrons. Okay, what's the question? Which ion is it? Well, we got to find out what the element is too. If it has a 23 electrons, but it's a 3+ charge ion, that means it has 3 more protons than electrons. The electrons can only neutralize 23 protons. That means it has 24, 25, 26 protons. So we go to our periodic table and we find 26 is that element, right? Iron. It's iron with a 3+ charge. There you go. How about this one? Certain ion X plus. Now we only have 1 plus. Has 54 electrons and 78 neutrons. Okay, what's the question? What's the mass number? Well, we got the neutrons. We need the protons. If we've got a +1 charge and 54 electrons, we have 1 extra proton. So that means we have 55 protons. So 55 plus 78 is, and 1 is 12, 13, 133. 133 is the mass number. Okay. Now, if we want to find out what element it is, we just say 55 is atomic number, and that is cesium. It's the cesium-133 isotope. Okay. Some compounds act like have molecules with single, they have a singular character like water or like carbon dioxide. But some compounds are formed from ions. These ionic compounds are actually not individual units of say sodium and chloride, acting independently. They're actually networks of those positive and negative, those cations and anions in a network. And our example here is sodium chloride. You can tell what the basic structure of the repeating unit is in salt, sodium chloride. All you have to do is spill some on a table, look at it with a magnifying glass. There are all these little cubes. So we've got chlorine here, chlorine here, chlorine here, chlorine in front, chlorine in back, then sodium here, sodium here, sodium here, sodium in front and back. It's a three-dimensional crystal network of cations and anions. Now, they have similar properties. They all have high melting points because of the strength of those electrostatic attractions. Very high melting points. They don't conduct electricity unless they've been melted, because the ions are locked into place. They can't move. If you don't have moving charges, you don't have conduction of electricity. So you have to either melt them or dissolve them in water in this case. Get those ions free from one another. Now they can move and they will conduct electricity. They're electrically neutral, right? The anion charges balance the cation charges. We're going to use that information to name compounds in the next chapter. All right. So if the chloride ion is always -1 and the magnesium ion is always +2, then it takes 2 chloride ions to balance the charge of 1 magnesium ion. That's why we write the formula MgCl2 to balance the charges. Now, that's not a molecule because these are ions, but this is the simplest whole number ratio of cations to anions in our compound. Okay. All right. We're getting close. A compound contains an unknown ion X and has the formula XCl2. Okay. Ion X contains 20 electrons. Okay. What's the identity of X? All right. The question requires that we find out the atomic number. So if these are -1 charge each, that's a -2 total. This has to be a +2. So that ion is 2+ with 20 electrons each. That means it has 2 extra protons. 22. So 22 on our periodic table says titanium. Titanium chloride is the name. Well, the ion obviously is Ti2+. This is a 1-, this is a 2+. All right. Let's see. A member of the alkaline earth metal family whose most stable ion contains 36 electrons forms a compound with bromine. What's the correct formula for the compound? All right. A member of the alkaline earths. So the alkaline earths always have a 2+ charge. And its most stable ion contains 36 electrons. So this is 36 electrons. But it has 2 extra positive charges, 38. Okay? So it's combined with bromine. Bromine's always a 1-, so that means we need 2 of them. So X has 38 protons, and we look it up. 38 is Sr, strontium. With bromine, 1- means we need 2 of them to balance the charge. So SrBr2 is our compound.